Okay, we want to return to the problem that we were just working on for confidence intervals and run a hypothesis test. What we would like to show is that the average price for hotel rooms in Cincinnati is less than the average price for hotel rooms in Nashville. To do that, I'm going to set up a null alternative hypothesis. Now, again, what I want to show is that mu1 is less than mu2. Now, another way of saying that is with a difference. Mu1 less than mu2 is the same thing as mu1 minus mu2 is less than 0. So in other words, if I can show that their difference is less than 0, I'm basically showing that mu1 has to be smaller than mu2. Now to set up a null and alternative hypotheses, I'm going to let the mu1 minus mu2 less than 0 be the alternative because that's what I want to prove. And if you remember, you'll never prove the null hypothesis. You're either going to reject it or do not reject it. So whatever is proven in a hypothesis test has to be the alternative. So I'm going to let mu1 minus mu2 greater than or equal to 0 be my null. And if I can reject that, then I'll prove the alternative, which shows that mu1 minus mu2 is less than 0, which says that mu1 is less than mu2. And I'll have a hypothesis test proving what I'd like to prove here. So step one of a hypothesis test is basically to set up the null and alternative hypothesis. Step two is I'm going to go ahead and think about what the sampling distribution on this looks like. For two population tests, the sampling distribution is a distribution of differences. And we're testing against 0. So the center of that distribution is 0, that there is no difference. And this is going to be a lower tail test. So with alpha equal to 0.05, I can get a critical value since I'm using also a standard normal here, because if you remember, the population standard deviations are known. I get a critical value of negative 1.645. And I'm going to go ahead and use the standard error. It's calculated with those population standard deviations. So this is something I calculated for the confidence intervals. So I got 20 squared over the sample size of 35, and 25 squared, the standard deviation for the Nashville rooms, squared divided by the sample of rooms that I took there, to get 5.2 as my standard error. Now, step 3 would be the rejection rule. So I'm going to reject the null hypothesis, H sub 0, if my test statistic, Z, is less than negative 1.645. And then I've got to calculate that test statistic, Z. So remember that the averages, and again, I'm taking population 1 to be Cincinnati's rooms and population 2 being Nashville rooms. So I'm going to take X sub 1 bar, the average of those 35 rooms in Cincinnati. The prices average to be $91.71. And X sub 2 bar, the average prices of the 40 rooms sampled in Nashville, turned out to be $103.02. So there is my point estimate, same one that I used with the confidence interval. Subtract what I'm testing against, and then divided by my standard error, which is 5.2. This gives me a test statistic, a Z value for my difference in sample averages, a test statistic of negative 2.18. And then, using my rejection rule, I can draw a conclusion. I'm going to reject h sub 0 since negative 2.18 is less than negative 1.645. So, I can conclude that the average price for rooms in Cincinnati is less than the average price for rooms in Nashville. That is a 5-step hypothesis test, very similar to hypothesis test for one population. The differences are that we are comparing two populations by looking at the difference in their averages, and we are combining variations from both populations into this test with a different standard error formula. Okay, now another way of running a hypothesis test, if you remember, is using a p-value. And I want to be able to calculate the p-value for this test and compare it to my level of significance 0.05. Hopefully, of course, to conclude the same thing, you remember that whether you use the critical value test statistic approach, which we just did, or whether you run the test using a p-value, both of these different ways will draw the same conclusion. Now, to calculate this p-value, I'm going to look at the test statistic, the negative 2.18, and that is the z-value for the difference in the sample averages. Remember that difference there is a negative 11.31. Now that negative 11.31 has a z-value of negative 2.18. So to locate it in the distribution, it's going to be to the left of my decision line, the line with the z-value of negative 1.645. So a negative 2.18 is smaller than negative 1.645. And my negative 11.31 is about right there in the distribution. Now, if the null hypothesis were true, the p-value is the probability of getting anything less likely than what we had. And to determine the p-value, I'm going to look up the negative 2.18 z-value in my standard normal table. The area to the left of that location is 0.0146. And that is the p-value. So to run the test using the p-value, I'm going to compare that 0.0146 to 0.05, and it's less than 0.05, so I'm going to reject h sub 0 and draw the same conclusion I did when I ran the test earlier. Now, in trying to interpret the p-value, remember that the sampling distribution in step 2 is built on the assumption that the null hypothesis is true. When we set alpha equal to 0.05, the level of significance, then if the null hypothesis were true, only 5% of the sample values that we would get when we sample from both populations and take the difference in the averages, only 5% of those sample average differences are to the left of that decision line. 95% of those difference in sample averages are to the right of that decision line. So I'm going to go ahead and shade that in green. So 0.95, 95% of the difference in those sample averages would fall in that interval on our sampling distribution. So I take a sample from population 1 and population 2, and I find the difference in those sample averages, and that difference is way down to the left in the sampling distribution, where only 5% of those difference in sample averages are. So, if the null were true, I should be in the green area. But I'm so far to the left of center that I'm willing to go ahead and say that the null is not true. I'm willing to reject the null. Now, when we set the level of significance at 5%, what we're saying is that we are willing to take a 5% risk in making a type 1 error. Now, the p-value, 0.0146, is less than 0.05. So we know that our risk in making a type 1 error is less than 5%. Now, we go ahead and reject the null. Doesn't necessarily mean that the null can't be right. It's just that it's very unlikely that it's right. It's like being in a courtroom. You just need to be sure beyond a reasonable doubt when you say guilty. It's not that you have to be perfectly sure or absolutely know the truth, but you need to have enough evidence so that you can say guilty, or that I can say that the null should be rejected, and be confident that I've made the right decision. Now, another thing that I want to mention here is to compare the confidence interval that we had earlier on this problem, which was negative 2150 to a negative 1.12. To compare that confidence interval with our conclusion in this hypothesis test. Now, if you remember, that was a 95% confidence interval. And what that would basically be saying is that we were 95% confident that the real difference in population averages would be somewhere between negative 21.5 and negative 1.12. We're 95% sure then that Cincinnati had the smaller average price per room, because both of those values from the left end of that interval to the right end are negative. 95% that the difference in the population averages is negative. 95% confident that Cincinnati has the smaller average price per room. That basically would tell us that the hypothesis test we just did would conclude with a rejection of the null. So what I'm trying to point out here is that a lot of times you can look at a confidence interval and see the outcome of a corresponding hypothesis test. We're going to be looking at several examples of this as we go further in this chapter.